Bloomy. And I've done a lot of hardware measurement abstraction layers over the years, and I wanted to do a twist on it this year in terms of, I think a lot of hardware HAL presentations are really focused on architecture, and I wanted to kind of take a step back and look at how the end user interacts with the HAL and how, and some lessons that we've learned throughout the years of developing our own HAL our EFT module for testing. So I'm going to go into a little introduction of Bloomy and myself, talk a little bit of background on what hardware measurement abstraction is, just enough to kind of frame up the presentation, and then get into some user profiles and who's actually interacting with this hardware measurement abstraction layer. And I'm using our EFT module for test stand as an example here. So the presentation is going to be a little bit more test stand geared just because that's where our experience is, but the implications here are much farther reaching. And then taking what the user profiles look like and how do we implement the user interface side or the user experience side of that hardware measurement abstraction layer to really focus things on the test developer rather than on the test architects. So Bloomy's been an alliance partner for about 25 years, really, since inception. We're located primarily in the Northeast, although we have offices, or we deliver systems all over the country and products all over the world. We're very highly LabVIEW or NI-centric. We are an NI reseller. We put out all of our engineers through some level of NI training. We also do a lot of systems geared towards battery test and simulation, BMS testing, aerospace and defense LRU testing. We're one of the pioneers of the SLSC architecture, and we've delivered, I think, 12 very large-scale high-channel count SLSC systems over the past few years. And some of those SLSC systems even use the EFT module for test data, which was originally developed for automated production tests, but it scaled well to the HAL testing as well. So I'm Chief Technology Officer at Bloomy. I've been there since 2007, testing a huge range of test systems from rocket motors to medical devices. And really my focus has been around hardware and software configurability. I don't like saying standardization, because standardization kind of makes me think of kind of getting stuck in a box and not really being able to get out of it, where configurability allows you to take standard pieces and put them together to make a system catered to what you need. And so as part of that, I've developed the EFT module for test stand, and as part of developing the EFT module, I wrote the white paper for hardware measurement abstraction that is on NI's website that's downloaded quite often, I believe. So, quick refresh on the basics. What are a HAL and a MAL? So a HAL is a hardware abstraction layer. It's essentially a way of defining how an instrument should behave. So things like a DMM or a switch matrix or a power supply. This is essentially what IB does. It provides a set of APIs or a set of functions that a particular driver should interface with. A MAL or a measurement abstraction layer is a step above that. And the measurement abstraction layer really frames out, in this case, a test from the point of view of the unit under test. It converts those instrument-specific functions into measurement-specific functions. Things like analog input or analog output or waveform input, where a waveform input is a type of signal which could be acquired from a DMM with a digitizer or an oscilloscope or a DAC card. It could be an NI device or a non-NI device. And so the measurement abstraction layer really frames out the test from the point of view of the unit under test. And so a really good example of this is printer dialogues. When you go to print from Microsoft Word, you don't go in and send the commands to the printer to print out the data. There's a driver for that. The printer manufacturer creates their drivers to follow a standard set of interfaces that a printer should follow. And so that's the hardware abstraction layer. The measurement abstraction layer is kind of the next step up, where it defines the actions that you should be performing with the printer. So setting landscape or color versus grayscale. But really, what we're talking about in this presentation is the user experience. And so really what we're talking about is the GUI, the user interface. And so on printer dialogues, this is essentially what you get. You give the options to the operator or to the person printing the document in a way that's easy for them to interface with and gives them a clean interface with the printer. So in test software, we essentially kind of have the same idea. At the top level, you have a test executive, in this case test stand. And when you're writing a test for test stands, you write them using your measurement abstraction layer. You create tests for things like analog input. And an analog input could be a voltage or a current or a temperature. It's scalar numeric data coming in. And then you have a mapping framework that translates the generic or the specific the signals that are specific to the unit under test to the interfaces that are specific to the hardware. So you can write your test agnostic of hardware as long as you know what those interfaces are. And so oftentimes I like to use an analogy. And so an analogy here is when you're working with hardware, you have some base instrumentation. If it's automated production test, it may be a PXI up to a mass interconnect. And you use a test picture to map that generic instrumentation to the specifics of the unit under test. So in a HAL now, you essentially have the same thing. You have generic instrument or specific instrument drivers for things like your NIDMM or your Keysight power supply or a chroma load. And you map those instrument drivers to the specifics of the test that you're trying to use through a configuration file. And that configuration file essentially allows you to define aliases from the point of view of your test or the unit under test and map those aliases to physical hardware configurations so that you can write your test using UUT-specific nomenclature. So the purpose of the hardware measurement abstraction layer in a test environment is to phrase the test sequence from the point of view of the unit under test. But for the sake of this presentation, we're essentially saying it's to make everyone's life easier. So the whole reason to put in all of the effort into a hardware measurement abstraction layer is so that you and your developers can more easily develop tests. And in the long run, you should have a net time savings. And so in order to make a net time savings, you have to know who you're developing for. And so oftentimes when we're talking about HALs and MALs, we're talking about people at the framework architect level. And so kind of taking a step back and looking at it, you realize that most of the people who interact with it are not architects, they're test developers. They care about their products. They want something that is easy to use and intuitive. And you have power users who are really looking for, they're essentially test developers or advanced test developers who may be able to contribute to the framework in small ways, adding drivers and stuff like that. And so they want a framework that is easy to use, but it's also accessible. It doesn't prevent them from doing the things that they want to do, especially those advanced features. And then framework architects want something that's flexible, so they're concerned with design patterns and how to extend functionality. So to kind of go through each one of these user profiles, test developers are your most common users, and I showed 10 plus users there. There could be in our EFT module we have 50 or 75 users. And so their focus is on implementing tests. The HAL, MAL, the test executive, all of that is really just a means to an end to get their product tested. So they want something that's reliable and easy to use, that has a low learning curve. If you can get them up and running in a day or two and frame everything out from the standpoint of what they're used to, talking to the product and talking to instrumentation in a way that they understand it without having to write code, then they're going to be much more successful in their job. Your power users are kind of test developers that are also framework contributors. So if you have a plugin architecture, they may be able to write new drivers for new instruments. At a more advanced level, they may be able to create new step types or new signal types that allow you to add functionality to the framework without modifying the core. And so they care about that advanced functionality. They care about kind of getting in behind the scenes to the APIs that the framework architects expose so that they can do some more advanced features or more advanced functions that sometimes the framework architects never even really planned out. And then finally, the framework architects are really thinking about design patterns, object-oriented coding, inheritance and extensibility, and all the things that most of the HAL-MAL presentations are really covering. So we're going to be focusing more on the test developers and power users as part of this, but talking about what the implications are for the framework users. So over time, the effort that architects are putting in should go down, and the effort that test developers are putting in to write their tests should go up, and actually over time that should go up faster and faster. And then your framework, your power users are kind of bursty. They're developing tests, but at the same time they may be adding a driver as needed, or adding a new piece of functionality, or adding a new utility to interface with the HAL-MAL in some custom way. And so really the architects are making bursts as there's new framework level versions created. And your test developers just kind of hopefully keep using it and using it and using it. So right over here, you're essentially looking at the early adopters, and then at some inflection point, your users or your test developers are using it more than the architects are interfacing with it, which is the case with our EFT module. I spent what was it, 2016, kind of walked in a cabin in Maine and re-architected the whole thing. So I was kind of at that top point. And at this point, I barely even open it anymore. I have a team of test developers, and we have a lot of customers who are using it. Once in a while, they may find a bug or something, and we'll compile a list of bugs and patches, and then release a new version. So those are those little peaks that you see there. All the time, we have some power users in our team who are adding functionality, drivers, and step types, stuff like that. So the thing to remember is that most test developers understand their instrumentation, they understand their product, but they're not necessarily software developers. So you want to make your HAL as accessible to them because they're the ones who are using it the most. So when you're trying to balance pure abstraction and the most best design patterns in the world versus some sort of usability, whenever we're thinking about this, I tend to lean towards, well, what's it going to look like to the operator? How do I make it more user-friendly for the operator? With the caveat being that you don't want to create Windows 8, which is so user-friendly that you can't do anything that you actually want to. So when you're architecting for that framework for the users, if we kind of look back at that slide with the hardware analogy, there's really three sections that we're focused on. The instrument driver development, and what does that look like, or what does the instrument interface look like? What does the mapping look like? How do you map that to the unit under test? And then how do you write your test using your HAL now? And so I'm going to start with actually the middle, because it ties everything together. The mapping is really where you define all of the I/O of your system and how you're going to interact with the unit under test and translate that to the instrumentation. So the key is to make it as easy as possible for the most people possible. And so when I started writing our EFT module back in 2010, we had an Excel configuration file. So everything was an Excel file. The structure hasn't actually changed, but we've gone from pages and pages of documentation of syntax. So if I was using a DMM, I'd have a string that told me how to implement a DMM syntax, or if I had a power supply from NI, I'd have a page of documentation for the NI power supply, or a Chroma power supply, or a Keysight power supply. And so as you develop that, it became difficult to add new users because they had to look at this documentation. It was very painful. So one of the things we did was we created a configurator. And so that configurator essentially allows you to map that instrument aliases to physical hardware. But from a normal test developer, it does it in a really intuitive way. So GUI-driven development, it gives the ability to filter and sort, remove in ways that they're used to interacting with things like Excel. Behind the scenes, it's still just basically building a tab-delimited text file, but it's doing it in a way that's very GUI-driven. We have filtered drop-down selections, so you can choose what kind of signal you're using and what instrument you want configured, and there's an instruments tab over there. And then only showing pertinent information. So in this case, we're showing an analog input using a DMM, and so we'll only see DMM-specific configuration parameters that pertain to an analog input. And so from the test developer standpoint, they can come in here, define all of the I/O for their system, for their unit under test, and do it in a way that essentially looks almost like a Mac soft panel. The power users use the same interface, but they may look at it slightly differently. So the power users may want to script configurations. And so in some of our large SLSC systems, we have tens of thousands of channels. You're going to go in here and click through all of this stuff that would be really, really painful. So whether you're using tab-delimited text or a JSON file or XML, if you have a well-defined methodology there and you're not just dumping a LabVIEW object to binary, you can script out a lot of this as necessary. Power users may want to define new types of signals. So for instance, we recently had a customer who wanted to do dynamic signal analysis for audio. It's a synchronized waveform output and input. It's not something that we had as part of the framework, but one of our test developers, or our power users, essentially created a new signal type that would end up being populated into that dropdown automatically as part of the framework, which is what we'll talk about when we get a little bit more into the framework architect side. The other thing is these instrument-specific configurations. So we release all the source code for all the drivers, and we provide plugin templates so you can create new drivers. So no matter what you're interfacing with here from your HAL now, you can interface with the drivers, and you have access to modify the drivers, what you interface with, how they get controlled, and how they get presented to the test developers. And then finally, when you're looking at it from an architect standpoint, what we're really doing here is a set of class extensions. And so at the top level, we have a generic abstraction. And so over here, we have instruments, signals, connections, communications. Each one of those things is a type of abstraction. And so whether I'm an instrument or a signal or a connection, I have an alias associated with me. And so then built off of that alias, if I go one level into the inheritance, we have signals. And signals have some basic information associated with them, like signal type and which instrument they're using, what abstracted connection aliases they're using. And that's all built into a signal type. And then there's different types of signals. So for instance, an analog input signal up here is going to have its own signal type specific parameters, like gain and offset, where a digital input may just have the ability to invert a signal. Or you may have a multi-IO where you want to define names with all of the inputs and outputs associated with it. So each one of these is actually an override in the class that gets populated into subpanels, and each one of those frames is a subpanel in the GUI. But it's all invisible to the test operator. All they see is a nice intuitive way to interact with the interfaces. And then down here at the driver level, it's not actually following that class extension. It's another implementation that allows us to plug in those driver GUIs into the HAL manager. So the bonus here is, with this HAL manager, not only can you configure all of the I/O associated with your system and map all of those aliases, but then you can go and there's a little drop down here for mode. And when you go into execution mode, you're now actually controlling that physical hardware, whether it's simulated hardware or real hardware. You can go in and check that your configuration properties were set up right, and hit execute and actually get a measurement using the exact same functions that you would use in your test stand sequence. So, test development. This is essentially using that mapping framework to write your tests. And so, one of the things that I want to say here is your HAL mal should complement the test executive, in this case test stand, not necessarily clash with it. And I'll kind of get into that in a minute. But essentially what we do is for each signal type in our manager, we have a step type in test stand. And that step type looks at that signal interface, allows you to put it onto your test stand sequence, and then there's an interface in test stand that you pop up to show what to allow you to select the alias that you want and configure the parameters associated with that signal type. So in this case, it's an analog input. There's not much to configure other than where does the measurement go. All of the specific configurations are done at the mapping level. So, test developer interface. So the test developer is using aliases to perform functions. So they want to interface with something that's really easy. You want to essentially make it so that they don't have to write any code at all if possible. So with these, each signal type has its own dialog and test stand. You pop it up and it gives you the ability to select an alias filtered dropdown. So if I have a power supply step type, I'm going to show only the signals in that manager that are defined as power supplies. If I have analog input, I'm going to show only analog input signals. Really easy to use interfaces. So showing it in a way that really makes sense to an operator. If they're making a connection, true or false. Maybe show the physical connection. If they're interfacing with power supply, show the voltage and the current in the enabled state. And you're really only exposing the most common features that they're going to use. There's different power supplies that may have different configurations. Anything that is device specific should be going into that mapping file. And we'll get a little bit into some more advanced functionality in a minute. Complex actions. So a lot of this is GUI driven, and so you can simplify a lot of what you're trying to do by doing error checking and looking for potential problems in what they're doing, or in this case, if they're creating a waveform and they want to make sure that it looks right, you can essentially show what that output waveform is going to look like before they even finish developing a test. So rather than having to go through and execute to a certain point and throw a scope on it to see what's happening, they can make sure that it's actually happening how they want it to before they even run their test. And then the other thing is to utilize test executive default conventions. So if you're taking a measurement, if you're using test stand, store it to step result numeric. That way, result processing all behaves properly. You don't have to change anything. You have that default convention right there, and it's kind of all just meshes into the test executive. So from the power user standpoint, we expose additional features. So for instance, if you push the more info button, it'll actually show you what's happening inside that configuration file. So you can see what instrument's being used, what COM port it's on, what the settings are associated with your gains and offsets. If you're using connections, it'll tell you which connections are being made. you can programmatically access those aliases. So when you have that alias dropdown, it shows you all the aliases associated with a power supply or a switch or a connection or an analog input. But say you had to make 100 different measurements on channels 0 through 99, and you wanted to iterate on that. It would be pretty painful to drop down a step type for every single one of those 100 connections, go in, open it up, hit the drop down, and click the next one. So we actually integrated test stand expressions directly into here. So if you have some local variables or parameters or something like that, you can define your alias building up an expression, and down here it'll show you how it resolves out to, so you can make sure that it works. And there's even error checking in there. So or parameters.channel doesn't exist, it'll actually pop up an error, the exact same one that it would show in a test stand expression browser. You can do that also with any programmatic access to parameters. So on the other side, I'm showing the power supply at the kind of the simple phase, but you can programmatically set anything that you can set simply using expressions. So here I have local.output current plus a half an amp, and so that's resolving out to 1.25. So output current is 3/4 of an amp. And so all of this is really just built into the application. And on analog outputs, you can pass that data. Look back here, we were using step result numeric as the default. Well, we actually have a drop down to say anything that's a numeric, you can pass that to. So if you wanted to pass it to a local variable or a parameter, you can do that. There's even, you can see a little browse button right there. And we actually pop up a dialog that shows the entire variable tree as it's seen at that point in the test sequence. And so you can browse through your variables as well, down into containers and anything else you might need to. So then at the framework level, at the architect level, we kind of break this down even further, and we realize that alias, no matter whether I'm talking to a connection or an analog input or an instrument or a power supply, I'm choosing the aliases in the same way. So I don't want to rewrite that every single time. So at the framework level, this is a generic alias dialog that implements all the functions I want for programmatic alias access and filtering. I can pass it, if I pass in a connection class, it'll filter it for connection. If I pass in a waveform input class, it'll filter it for waveform inputs. And then it'll populate the specifics of it based off of that class. So each of those classes implements the alias or the test stand dialog interface. And I can create this test stand dialog interfaces for each one of my signal types so that the operator, when they're looking at it, has kind of the seamless view of the world. It all kind of makes sense. It's really intuitive to use. And then all of the signal types are all plugins. And so this actually makes deployment a lot easier. There's a base core configuration for our hardware access framework. And then each set of signal types is its own packed project library. So right here I'm showing what we call our standard signals, analog inputs and outputs, digital I/O, waveform I/O counters. And so that gets built into a packed project library and stored with the file. We have another PPL for power supply stuff. We have another PPL for multiple analog inputs and communications. We're building one right now for robotic motion control. And so each one of these can go into the folder. The framework doesn't need to know anything about what signals are going to be there. But you can create new ones, drop them in, and the whole architecture will just work as long as they follow the conventions of the classes. So a couple tips here. The more you can follow your pre-existing test stand or test executive conventions, the easier this will mesh into the architecture, and the easier it'll be to use. You're using the conventions that people already know. NI has training on test stand. Most of that pertains to our hardware access framework as well, including variable locations, step types, test types. So if you can implement it as a numeric limit test, everyone who uses test stand understands the numeric limit test. You're using the limits files, or the limits tabs, limits files. It makes everything really make sense, and you're really only focusing on the parts that are custom or specific to your particular framework. And if you're following all those conventions, then your result processing becomes really easy because it just plugs right in. If you're using the HTML or XML result processing plugins, great. If you're creating a custom result processing plugin, it works as well. As long as those result processing plugins are using the test stand defaults, then everything that you create as part of your HAL now will just mesh perfectly into there, and you don't have to worry about logging to TDMS files in one situation and having test stand generate as HTML file in another situation. Sequence file attributes. So when we look back at this configuration file, the test stand sequence needs to map to that so that when I click on this, this is coming out of test stand, a if I click on that drop-down, I need to be able to see what's in that alias or mapping file. And so what we do is we use sequence file attributes to store the link to, or the path to where that file is. And so now that test stand sequence file is linked to the mapping file. If you change the mapping file, all of your step types can automatically be updated and look, and the drop-downs are repopulated with the new aliases that you have. And then implementing test stand expressions and API calls directly into it as much as possible really makes for a seamless integration with test stand or whatever other test executive you have. The more you can integrate that, the more seamless it'll feel. It'll feel like a much better product, and it'll get more wide adoption. The only issue there that we find is actually we find ourselves supporting test stand more than we support our EFT module, because it's so seamlessly integrated that especially new users who just kind of start off using test stand with EFT don't really know where test stand ends and EFT begins, and so we end up supporting test stand questions more than EFT questions. So then the last piece of the puzzle is the instrument drivers, and which are, when we create a new instrument driver for a customer or for a new device, typically takes somewhere between 8 and 16 hours. And I would say 2/3 of that is the GUI development. So if you think of the mapping framework, how do you make it so that no matter what signal type you're using, it looks nice to the customer? So in this situation, to the test developer, in this situation we have an analog input with a DMM, and we're showing analog input DMM specific stuff. I could also do an analog input with a DAC card, and I see DAC specific stuff like minimum value and reference signal ended versus differential, where the DMM has DC volts, resolution, and range. But they're both analog inputs, and from the standpoint of writing a test stand script, all I'm doing is I'm just calling the signal alias. And so test stand doesn't care about what instrument I'm using. So then I have the DAC with an analog input configuration. I could also use the DAC as a waveform, and I have different parameters here in terms of triggering and what the clock rates are, and how I'm interfacing with how many samples and sample rate. And then I can still keep a waveform input and change it to a scope, and I get different parameters like what's my trigger edge, and what's the horizontal spacing, and what's the vertical spacing on the scope. And so whether I'm taking my measurement through a DAC card or a DMM or a scope, the waveform input from test stand all looks the same. And so we're really just showing the information as the customer expects it from the point of view of the instrumentation and the point of view of the test sequence. As we dig deeper into it and provide that higher level accessibility to our power users, we essentially provide a driver template so that new drivers can plug into this architecture very easily. And so first part of it is the configurator GUI, and this is probably where most of our time is spent when we're creating a new driver. Because you want it to be easily usable, error checking, and making sure that they're not creating parameters that would damage the system or throw errors. You spend a lot of time trying to make sure that all of your drop-downs and enums and all that kind of stuff flows really nicely. But we provide the templates for doing that, and it's a simple producer-consume. We have driver base. This is really, if you think of the printer, this is where you're sending the bits and bytes to command something. And so this is, in our template, is actually a simple action engine. And it doesn't have to be a simple action engine, but in our template we do it that way because most of our customers are test developers who are working with relatively simple or very limited LabVIEW knowledge. And then finally we have the interface functions. And the interface functions just call that driver base. And those interface functions are really defining the front panel controls and indicators. Because in our architecture, all of the drivers are called through VI server. And actually, I'll get to that in a second, or right here. So in the architecture, all of our drivers are called through VI server and they follow that plugin template pattern. And this is one that's kind of been a legacy, and we have a lot of customers now saying, why aren't the drivers object-oriented? Why are they so rudimentary? And when we developed this back in initially 2010, 2011, LabVIEW object-oriented was not widely adopted. It was a scary thing. We were trying to cater this to our customers. And so over time, we developed a plugin architecture. We've added new features, but we were trying to maintain a lot of backwards compatibility. Now, with the wide adoption of object-oriented programming, most of our customers, or at least our power users, won't have a problem with that, and we're currently re-architecting our plugin architecture to be able to support more class-based drivers. But for right now, that's one design decision that kind of stuck with us a little bit longer than we had intended. But the nice thing there is we have customers who can write all their own drivers without ever having to modify our framework. So at a accessibility level, we do have a bonus backdoor, which is with all of our instruments, we have the ability to, from testband directly, get the instrument references. So even though the hardware access framework is handling all the initialization, all the references internally, we provide a step type that just says, okay, I have my DMM, I want to get the reference and pass it to this file global. And then I can write code to do anything I want to. I could take in the reference from a DMM and a DAC and a power supply and trigger on a power supply going high and grab a DMM value. So once again, this is kind of sort of a backdoor. It gives that extended accessibility for power users to be able to access what they need. And then at a slightly higher level, we have what we call custom instrument actions. And so say you have a power supply that has, an AC power supply that has a transformer. It's not something that's necessarily going to be abstracted in a generic way for all power supplies, but it's something that your power supply has access to. You could get the reference and call a VI, write a VI to send that command, or if you look back at our plugin template, each one of these interfaces, you can actually have custom interfaces. So you could create a custom interface here that just has a Boolean that says AC power supply transformer on or off. And we can call that directly from these custom instrument actions right from testing. And so you can create custom actions for power supply slew rates or clearing your DAC tasks, or really whatever you want to, that's specific to a particular instrument. It's not abstracted, but it means that it still flows through the process of developing your test in the same way that calling an analog input would. So just to recap, pretty quick. The purpose is really to increase adoption. If you're creating a large-scale hardware measurement abstraction layer, it really only pays off as that test developer curve goes higher and higher. And so in order to increase adoption, you have to reduce the learning curve, you have to make it much easier to use, and you need it to mesh well with all of the other features of the framework or of the test executive. Test developers are not software developers. Once again, oftentimes they just want to get their product tested as fast as possible and as easy as possible and reduce maintenance costs. So if you produce something that is cumbersome to use and difficult, they're going to find something else. The mapping, it ties it all together. And so in our framework, I think we probably, in terms of the GUI interface, I would say at least half of all of our effort was put into that mapping architecture, into the GUI architecture for them. But in the end, it means that we have a lot more people. It's more accessible to a lot of our customers. I can take a customer who's never opened testing before, who's never written an automated test, and in 2 days I can teach them 1 day of testing and 1 day of EFT and have them going off and writing test sequences. And I have a few customers who are strong power users, verging on architects at this point. Because that low barrier to entering them, they can start writing the test and they can slowly grasp the new concepts rather than starting from scratch, having to write all their drivers, potentially learn object-oriented programming to interface with other HALs and MALs. This gave them the ability to kind of start up, get running quickly, get their products going, and then add on to their own implementation of the framework as they went. Complementing the test executive is a really important one. The more you can mesh into the test executive, the less you have to write on your own. So testband has a billion built-in features, and we don't want to rewrite all of them. So expressions and result processing and interfacing with the unit under test and flow control and all of that kind of stuff. The more we can let testband do its thing and just kind of complement it, add in the features that we need, the less we're writing testband, the more we're focusing on the instrument interfaces and through part of the hardware measurement abstraction layer. And then finally, the GUI is by far the most time-consuming part. I recently wrote a 3-phase AC power supply step type, and the object-oriented part, the interfacing with or defining all of the I/O for a generic AC power supply was easy. Writing a way to make sure that all the parameters were set up right, and if you set 2-phase, you didn't have something trying to command the 3rd phase of a power supply. All of those kinds of things probably took, in this case, 80% of my time in just trying to implement all the expressions and make it really easy to use. But now that it's really easy to use, I don't have to think about it anymore. And I can have one developer writing an AC power supply for pack power and another one doing it for Keysight. And I don't have to think about it anymore as a framework architect. So it really makes the whole architecture much more accessible. Any questions?
test systems, is all configuration for the test system found on buying shows, or are they?
So technically, that configuration file is really just for the instrument mapping. And actually, if you look right here, there's some stuff up here in blue. And so this architecture actually has the ability to link configuration files. So this is actually using a system configuration file that defines the max aliases and the COM ports and some generic system definition things for like fixture ID and lid detection that all of the other ones can link to. So all of my units under test can link to that and automatically get all those configurations. And then if I have multiple test systems and my DMM card over here is called Dev1 and my DMM card over here is called DMM 4071, I don't have to go about and update all of my test sequences according to that. I just have that one file that modifies it. The one caveat there is if you change the driver that you're using, so if I'm using a Keysight power supply over here and an NI power supply over here and my drivers configurations are different, if you modify that, you may have to make some updates to each of your UUTs to be able to, because these parameters down here are specific to that particular instrument.
And regarding that, how do you handle it? One specific instrument also change what is possible to set up according to, if you take Keysight voltage, then you have one set of possibilities, but if you take AC voltage, you have another set of possibilities.
So that's why the GUI development takes the longest. And actually, I'm not showing it here, but in the measurement type here, we have thermocouple as well. And as soon as you choose thermocouple, it gives you possibilities for what type of thermocouple and a few other options. Or I said it gets temperature, and then when you choose temperature, it says thermocouple or RTD. And when you choose thermocouple or RTD, it gives you more options. That's all just coded into event structures. It's all hard-coded as part of that driver interface. So that's why it's so time-consuming.
Yeah, and I've seen a lot of sessions for these all in mode, but I have never seen an example for an advanced oscilloscope or vector analyzer or anything.
Yes. I do have, I'm showing one, where is it? There was one that showed a scope configuration. It got pretty, there we go, right there. So this is an NI scope, and we have a lot of tabs there. And we even have some of our customers' proprietary instruments where we can't even fit it here, and we actually just pop up another dialog that's got a wide range of configurations. And you can't really tell. In this framework, all of this gets boiled down to some kind of string. It could actually be a binary string. We typically like to make it human readable so that we can script it if needed. But this string right here is very long if you actually showed it. And so when you talk about a vector signal analyzer, you may be better off just dumping that to binary because that's going to end up being so long that it's almost cumbersome. More questions? If anyone's interested, we have this demo on the floor, booth 123. I can actually say that this is the first time in a while I haven't had a presentation on booth today. So stop by the booth and I can give you a demo, and if you have specific questions on how we do certain things, I'm happy to open up the code and dive deep into it. Yep.
Of the three roles, which one, or do you find that the configuration is changed frequently by test developers, or?
In most cases, it's our test developers. So in our typical workflow, when we have a test to develop for a customer, we'll sit down, we'll look at all the I/O of the unit under test. We'll look at the test. Actually, we'll go through the test procedure, and we'll frame this out. And we may not even know what instruments we're using yet, but we can frame out that mapping file and say, okay, I know that I have a 24-volt input, so I'll call 24-volt input. It's going to be a power supply. I know that I need to measure the resistance of these three rails. So I'll put, rail 1, 2, 3 resistance measurement, and those are analog inputs. And so for the most part, the test developer is doing that. Some of the more advanced test developers may be modifying the drivers, but not typically. Most of the time it's at the test developer level. And in some cases, we even have the the electrical designer framing this out based off of the fixture wiring, and then the test developer is going in and filling in some details about how the instrumentation works and writing the rest of the test sequence. Yep.
So at this level, you're writing essentially a signal, and it has some settings for your instruments. And then in test stand, they can then override some of those. How do you get kind of the mapping of what you chose on this screen compared to what is then selectable on the other screen?
So let me see if I get a go through them side by side. So really, we try to make a distinction where anything that is, here we go, anything that is instrument specific goes over here, and anything that is generic to the signal comes over here. So really, we don't allow easy override of those parameters from testing. So if you wanted to take 2 PM measurements of the same point, one at DC volts in a 100 volt range and one at DC volts at a 1 volt range, you would have 2 lines in here associated with that. And for defining new signal types, one of the harder parts is really defining especially if you have like a sample set of 1 per instrument. What's instrument specific and what is instrument generic is really a fine line to define sometimes. Yep.
Are you looking at user roles, deciding what to modify?
Yeah, I mean, we typically are looking at user roles from the standpoint of the test developer. In terms of what they're allowed to modify, we expose most of the API. So as part of the framework itself, most of the ability to control things is exposed with a small subset of kind of secret sauce that ties it all together. If you broke it, the whole thing would crumble. But in terms of the signal types and what gets plugged into here and how all of this is defined, even at a test developer level, they have access to it. It's just they have to kind of pull the curtain away to look at it, and it requires some active documentation reading, essentially. Yep. So right now, internally to our company, we have about 20 or so people using it. We have, I want to say, 20 or 30 active customers probably using it as well. Yeah. At various levels. So there's everything from our early version, which was Excel-based, which we still have a couple customers who aren't changing anything because it works and want to change it, all the way up to the latest version. We'll be releasing a version 2018 or 2019 relatively soon as well. Yep.
Are you looking into doing customized test stand GUI interfaces for this extensions via .NET, I think, right? For the
You mean so that go down kind of in the bottom part?
Yeah, so
We've kind of investigated it, but we haven't had the time to put into actually implementing it at this point. It's definitely something we've talked about over and over and over again, but pulling the trigger on investing the time to do it has been difficult. So this is sold as a product. So we build versions of this with the core functionality. All of our drivers we release with source code, and all of the step types, if customers ask, they can have the source code. It's just we don't supply it with the source code for the step types, just because it's a bit more advanced. So that being said, one of the things we suggest to our customers is if you're taking our DMM driver and modifying it, we suggest you rename it, because if you install the next version, it's going to overwrite that. We install with driver-wise, we install with mostly NI drivers, and then we have a download page that gets you vectoring switches and Xantrex power supplies and whatever else you might need. Any more questions? Awesome. Well, thank you very much. Stop by the booth if you're interested in more.